Hello everyone. In this video we're going to be taking a look at another characterization of completeness for R, and it's called the cut property. And this property tells us, well, it's stated here, just say that if A and B are just some non-empty disjoint sets whose union is R, so you partition R essentially into two sets, where one is strictly, for all elements of A are strictly less than all the elements of B. Then there's some C, which is kind of like halfway in between the two of them. So maybe I'll draw a little picture. Okay, we have our real number line. We have maybe A like this. And maybe it goes on forever, really, right? Because it has to, the union has to be everything. So we have A kind of like this. And we have B kind of like this. Remember, the union has to be R, right? So it has to kind of cover everything. There can't be like a gap there. And there exists some, the claim, the cut property is that there exists some element C in R such that C is greater than or equal to everything in A and less than or equal to everything in B. So there's something in between these two sets like that. These two, we call it a cut of R. And so we're going to use the axiom of completeness to prove the cut property. So taking a look at this, right, the axiom of completeness tells us that there is a supremum for every non-empty set that's bounded above, and it also tells us from our last video that there is an infimum for every non-empty set that is bounded below. Did I say below before? Let me just make that clear. Axiom of completeness. Every set that's bounded above has a supremum. Every set that's bounded below has an infimum, non-empty. So, well, we need to somehow use that fact to kind of generate our C. So C is clearly going to be the supremum of some set, or the infimum of another set. In fact, it'll be both. So we have that, we're going to say C is equal to the supremum of A, which is the supremum, which is the infimum of B, right? So if these are equal, we're going to show this, right? But, if these are equal, then C works like this, right? So, basically, that's the claim. I might just rewrite it. So claim supremum of A equals the infimum of B equals C. And it, maybe we could say then, we immediately get that, for all A in A and B in B, we have that, well, A is less than or equal to C because it's the supremum, and B is greater than or equal to C because it's the infimum. And we get what we want essentially, which is the final part of this kind of statement here. That too. So we just have to show that with this setup where the union is R and one is strictly less than the other, and they are disjoint, non-empty, then their supremum and infimum must line up. And then that's going to be a real number by the axiom of completeness. Okay, not too hard to show. So show, maybe we can kind of, suppose that the supremum of A is strictly greater than the infimum of B. So they are not equal and they're strictly greater. So there's some gap there. So we can say that maybe A goes up to some supremum, and B, supremum of A is strictly greater, right? So B goes down. So maybe B goes down to the infimum of B. So we have a little gap there. We have maybe a little overlap. Maybe not gap, maybe it's not the right word, but we have an overlap. Okay. Well, there's some kind of contradiction we have to find here. And this is the contradiction, right? So since um, well, we have the infimum of B is the greatest lower bound. This tells us that for all epsilon greater than 0, there exists a B in B such that B is greater than the infimum of B plus epsilon. Less than, I guess, right? Less than. So what does that mean? That means that choose any epsilon that I want here. If I go any higher, so infimum plus epsilon, I'll be able to find some element of B in there. And then similarly, since supremum of A is least upper bound, this tells us that for all epsilon greater than 0, there exists an A in A such that A is greater than infimum supremum of A minus epsilon. So for any epsilon I want, I can go to the supremum and I can go a little lower, and I'll always be able to find something in that range. I'll draw this picture a little bit bigger, right? So we have the supremum, which kind of goes up to here. So this is the supremum of A. And here we have the infimum of B. And so my claim is that, well, not really a claim, but the fact we know about the infimum supremum is that if I go any epsilon amount this way, right, I'll be able to find some element in here. Some element of B in there. And that's a problem, right? So if I find an element B in here, let's say I find some B prime, then what that means is that from the other side, the supremum side, I can maybe go this amount, this epsilon down, and I can find some A here, maybe A prime. And this contradicts what we said, which is to say that A is strictly less than B for all A and B and B. Well, this contradicts it, right? Okay, so we get a contradiction here, right? However you want to state it, maybe you can go halfway here and halfway there, and then you'll find something. But this distance here is non-zero. Okay, so that can't happen. Now suppose that the supremum of A is less than the infimum of B. Okay, so that means that we have our supremum going up to some point here. Might or might not be in the set, doesn't really matter. And then we have our infimum of B. And so then, again, we can kind of consider, well, this is a real number. This is a real number. Let's think about what the real number is that's right in the middle. Infimum of A plus infimum of B divided by 2. Call that maybe, well, I don't know, call that maybe C prime or something like that. So C prime is equal to the supremum of A plus the infimum of B over 2. Well, C is greater than the supremum of A, right? Therefore, C is not an element of A. C is less than the infimum of B, which means that C is not in B, which contradicts the fact that we said that A union B is equal to R. And we are essentially done this side of the proof, because we've shown that the supremum of A must equal B, and you can take that as some real number, and that real number there satisfies the properties that we want of the cut. We're going to prove the other direction as well to show that this is an equivalent formulation of the axiom of completeness, or the equivalent characterization, or how should I say it, equivalent logically to the axiom of completeness. So we show that the cut property can assume the cut property, prove axiom of completeness. So we take R, assume that it possesses the cut property, let E be some arbitrary non-empty set that is bounded above, prove that the supremum of E exists. Okay. So E is, all we know about E is non-empty and bounded above. Okay. So if we take B to be basically X such that X is, let's say, a strict upper bound for E, then we can conclude, which maybe another way of maybe saying this is that X such that E is less than equal to X for all E and E, then we know that B is non-empty, right? So B is not equal to the empty set because E is bounded above. So that bound, is possibly not strict, but then certainly that bound plus 1 is greater and would be strict at that point. Okay, so it's not empty. And remember what the cut property is telling us. The cut property tells us that if we have two sets whose union is all of R, and who has this property that A is strict less than B for all A and A, B and B, then we can conclude something. Okay, so, well, I know that B complement union B is equal to R, essentially by definition of complement. And let's just, maybe say, let A denote B complement. So we know that A union B is equal to R. We just have to show now that for all A and A and B and B, A is strictly less than B. Okay, maybe I'll say that as a claim here. Since we have that, let's just, we'll prove the claim in a second, but just since we have this, then there exists a C in R such that A less than equal to C less than equal to B for all A in A, B in B. And then the further claim is that the supremum of E is equal to that C. Okay, so we know that C exists, and the claim is that the supremum of E is equal to that. So we have claim 1, claim 2. And so, with the claims we're done, but let's prove the claims, right? So proof of claim 1. Well, basically has to be true. So B, okay, so we know that A is in A, which is B complement. And we know that B is in B. So, okay, so we know that B is a strict upper bound for E. Okay. So that means that B is strictly greater than E for all E in E. And we know that A is not in B, which means this property is not true, which means A is less than or equal to E for all E in E. And basically follows. B strictly greater than E, less than or equal to A. So we get that B is strictly greater than A. And we get our claim. And then we need proof of claim 2. Okay, so claim 2, we need to verify the properties of supremum, right? So if we recall, supremum is the supremum of a set is equal to some number if, well, first thing we have to show that C is an upper bound for E. Okay, and that's pretty clear because we know that C is an upper bound for A, okay, and E is a subset of A. Right? So since E is a subset of A, we have that since for all A in A is less than or equal to C, well, then we get that for all E in E is less than or equal to C because E is in A. And we know E is a subset of A because take any arbitrary element of E, it certainly can't be in B the way we've defined B, right? Because we're thinking about all the strict upper bounds. So it's in the complement. A is a complement, right? Okay, so that's it. And then for the second part of the supremum, right, we have to say, suppose B prime is any upper bound for E. Show B prime is greater than or equal to C. Well, if B is any upper bound, okay, so B, first of all, could be strictly upper bound. Well, if B, we know, right? We know that for all B in B, B is greater than or equal to C. And we basically have our result here, right? Because the B prime being any upper bound of E, that means B prime is either in B, in which case we already have our result, or B prime is equal to C, right? Because C is an upper bound for E. And, well, then, clearly this is also true because then they'd be equal. And so there we go. There's proof of our claims, and we can draw our little box. And so we've essentially shown here that the cut property of the real numbers is equivalent to the axiom of completeness stated as our usual kind of starting place for completeness in R. That's all. Thanks for watching.